Hi students, in this video we are going to discuss about the design of the springs. A spring is an elastic object used to show the energy, mechanical energy. The springs are elastic bodies that can be twisted, pulled or stressed by any force. They can return to their original shape when the force is released. So a spring is a flexible element used to exert a force or a torque, and at the same time it shows the energy. The torque can be used to cause rotation, for example, to close the door on a cabinet or to provide a counterbalanced force for a machine element pivoting on a hinge. The objective of the springs is to provide a cushioning, to absorb or to control the energy due to the shock or vibration, to control the motion, to measure the forces, and to store the energy. The helical springs, it is made up of wire coil in the form of a helix having a circular, square or a rectangular cross section. You can see the free length, the coil dia, size of the material, and you're going to see from the top, I'm going to see the circular shape. So what is the procedure you want to follow for designing? The procedure what I want to explain is for the circular helical springs. The design procedure, the first step will be diameter of the wire. So shear stress tau is equals to 8FDK pi d cube. So where K is nothing but the Val's stress factor 4C minus 1 divided by 4C minus 4 plus 0.615 by C, or K you can take from the figure 20.5 from the data handbook. So where C is given by capital D by small d. So where small d is the spring diameter of the spring wire. So from table 20.12, select the standard diameter of the spring wire. So once the D value is known, so select a standard value from the table 20.12. The second step will be finding the diameters, the mean coil diameter, D is equals to C into small d. Outer diameter of the coil, D0, capital D minus plus small d. Inner diameter of the coil will be Di, that is capital D minus small d. So number of coils, so we're going to find out using axial deflection Y. So it will be 8FD cube into I divided by D to the power of 4 into G, where I is number of active turns or coils. The equation number will be 20.29. So we want to find out the free length, that is length of the spring. So free length L should be greater or equal to I plus N into D plus Y plus A. So clearance A is equals to 25% of the maximum deflection, or A I minus 1 into gap between the adjacent coils, and Y will be the maximum deflection. Assume a square and ground N. So therefore number of additional coils N is equals to 2. The stiffness or rate of spring, the stiffness of spring Fn is given by F by Y, that is this to the power of 4G divided by 8I d cube. The equation number will be 20.30. Pitch. So pitch P is equals to L0 minus 2D divided by I, or L0 divided by I minus 1. So from the table 20.14 you can select the values. Rp is equals to Yx divided by I plus D. So for an actual frequency of vibration of helical spring, so you can use the formulas, that is 20.75 and 20.76 for F. That is the frequency. Mass M, you can use the formula volume into mass density, where volume will be given by pi capital Di multiplied by 1 by 4 pi d square. So weight is equals to volume into weight density, that will be given by pi square into d square Di by 4. The factor of safety based on the torsional yield strength. So you can use the formula and you can find out. So let us go for the problem. Design a helical compression spring to support an axial load of 3000 Newton. The deflection in the load is limited to 60 mm. The spring index is 6. The spring is made up of chrome vanadium steel and factor of safety equals to 2. So F is equals to 3000 Newton, Y is equals to 60 mm, C is equals to 6, that is the spring index, and FO is equals to 2. So from the table 21.10 for a chrome vanadium steel, tau Y is equals to 690 megapascals, so 690 Newton per mm square, that is 0.69 GPa, and G will be 79 GPa, that is 79,000 Newton per mm square. So tau is equals to tau Y by FOS. FOS are going to given as 2, so 690 by 2, you are going to get as 345 Newton per mm square. So diameter of the wire, so shear stress tau is equals to 8FDK divided by pi d cube. So K value will be 4C minus 1, 4C minus 4 plus 0.61 by Y C. So C value is given. So I'm going to say take C value as 6. So by substituting this, I'm going to get a factor as 1.2525. So spring index C is given. So capital D by small d. So capital D can be written as 6 times of the diameter of the wire. So I'm going to substitute that and I'm going to get a small d value as 12.89 mm. So from the table 20.12, the standard value will be d is equals to 13 mm. So diameter of the coil, so C is equals to d by d. C value is given 6. So capital D will be equals to 78 mm. That is the mean diameter of the coil. So outer diameter d naught. So capital D plus small d, that I'm going to get as 91 mm. Inner diameter of the coil di, that is capital D minus small d, I'm going to get as 65 mm. So number of turns or coils, so deflection y is equals to 8f d cube into I divided by d to the power of 4 into g. So I'm going to get y, they were given as 6. F value is known, d value is already found out. So I is unknown, d value is known, and g value is known. So by substituting this, I'm going to get I is equals to 11.89. So that I want to take number of active turns as I is equals to 12. Free length L naught greater or equal to I plus N into D plus Y plus A. So N is the number of additional coils. So for additional coils I want to take as 2. So clearance A, 25% of the maximum deflection, 25 by 100 into 60.313. So I want to get as 15.078 mm. So actual maximum deflection Y is equals to 8 into 3000, that I want to take as 560.573 mm. So actual free length L0 will be equals to, substituting all the values over here, I want to get that one as 257.72 mm. Coming to pitch, P is equals to L0 minus 2D by I. So L0 value is known and 2 into D value is known, I value is known. I want to get pitch as 19.31 mm. So required stiffness or required rate of springs, that is F0 is equals to F by Y. So F is given and Y is known. I want to get as 50 Newton per mm square. The actual stiffness or actual rate of spring, so F0 is equals to D to the power of 4 into G divided by 8I D cube. So substituting all the values, I want to get that one as 49.53 Newton per mm. So what are the specifications you are going to get? So my material is chrome alloy vanadium steel. Chrome vanadium steel, mean coil diameter is 78 mm, total number of turns is equals to 14, pitch will be 19.31, actual rate of spring F0 will be equals to 49.53, wire diameter D is equals to 13, free length will be 257.72, style of end will be squared and grounded, required rate of spring will be F0 is equals to 50 Newton per mm, the actual maximum deflection will be 60.573 mm. Coming to the next problem, helical valve spring is to be designed for an operating load range of approximately 90 to 135 Newton. The deflection of the spring for a load range is 7.5 mm. Assume the spring index of 10 and factor of safety as to design the spring. The maximum load F2 is 135 Newton. The minimum load F1 is 90 Newton and Y dash is 7.5 mm and C is 10 and F2 is 2. So assuming the chrome vanadium alloy steel, so from the table 21.10, yield shear stress will be 0.69 GPa or 69 MPa. So and G value will be 79 GPa. So finding the shear stress, I want to get as 145 Newton per mm square. So her maximum deflection Y is equals to, so we're going to take the value, I want to get as 22.5 mm. So design the spring for a maximum load and minimum, so maximum deflection. So diameter of the wire, shear stress, tau is equals to 8F2dk divided by pi d cube. So by finding the k value using C, I'm going to get as k value as 1.1448 and C spring index is also known as C is equals to D, capital D by small d. I'm going to get capital D in terms of small d as 10D. So substituting that, I want to get small d as 3.37 mm. So for this, the standard value of the diameter of the wire will be D is equals to 3.4 mm. So diameter of the coil, so mean diameter capital D is equals to C into D. So I want to get as 34. Outer diameter D naught, I want to get as 37.4. Inner diameter will be 30.6 mm. So number of coils, equation number 20.29. So Y2 is equals to 8F2D cube by I d to the power of 4 into g. By substituting this, I want to get I as 5.6. So I want to take the number of active turns as I is equals to 6. The free length L0. So I want to go for the equation 20.53. So greater or equal to I plus n multiplied by d plus y plus a. So a is the 25% as the maximum deflection. So maximum deflection is 24.125. So I want to get as 6.03 mm. So assuming the square and ground end, so number of additional coils will be equals to 2. So total number of coils will be I plus 2. So that is 6 plus 2 is equals to 8. So actual maximum deflection I want to get as L is equals to 24.125. By substituting this, I want to get L0 as 57.355 mm. So pitch P is equals to L0 minus 2D by I. So pitch I want to get as 8.426 mm. So required stiffness or required rate of spring will be F0 is equals to F2 by Y2, that is 135 by 22.5. So I want to get 6 Newton per mm. The actual stiffness F0 is equals to D to the power of 4 G 8I d square d cube. So I want to get, while substituting all the values, I am going to get as 5.6 Newton per mm. The total length of the wire L is equals to pi d into I. So I is equals to I plus n, that is 8. So if I were to substitute the values, I am going to get as 854.513 mm.